Hey everybody, so this is a brand new topic on oscillations. So let's go through a few examples. So let's say you have a spring connected to a mass over here, and then let's say this surface is smooth. And say I grab this block and move it over here, and then let it go. What's going to happen? It's just going to bounce back and forth like this, right? It's going to bounce back and forth forever because the surface is smooth. And if we ignore air resistance and all that, that's not what we experience in life, right? So this is kind of an idealization. And I'll just call this, say, the x direction. And let me just make up numbers. Let's say the mass is 1 kilogram, the spring constant is something. And let's say when I start my stopwatch, let's say the block is at some position 0.1 meters. So it's somewhere like over here. And then let's say the initial velocity, so the velocity at t equal to 0 is something. I'll just make up some number. Okay, so we're given all this information. Now, let's solve for the position. The position as a function of time. Okay, how do we do that? So if we draw the free body diagram, right, it looks like this. If it's over in the, let's say here's y. If it's over on this side in the positive x direction, then the spring force would be this way. When the block is on this side in the negative x direction, then the spring force would actually be the other way. So this is if it's over here on the positive side, the spring force. Okay. So in the x direction, minus spring force, so k, and then the displacement, x, equals mass times acceleration. In the y direction, okay, and this would be 0. Let's focus on this one. I'm going to just erase this. Okay, so you see how the acceleration, let me just divide both sides by mass. The acceleration is proportional to the displacement with this minus sign over here. So whenever that is true, this is called simple harmonic motion. Simple harmonic motion. The acceleration is proportional to the displacement, but in the opposite direction. That's simple harmonic motion. And then a system like this mass spring system, subject to simple harmonic motion, would be called a simple harmonic oscillator. Okay, but how do we solve? Like, how do we solve for x? Notice that, let me point something else up. Let me move this back on the other side. Okay, acceleration is the time derivative of velocity. Right? And then velocity is the time derivative of position. So I could replace acceleration with this second derivative. So look at this. This is called a second order ordinary differential equation, which you would just say ODE. Second order ordinary differential equation. Ordinary, well, differential equation because there's a function x and its derivative, its second derivative. And the order of that is 2, so that's why it's second order. And then ordinary just because, as opposed to partial derivatives, like if x were a function of multiple things, then you could take a partial derivative with respect to one of its variables. But in this example, x is only a function of one variable, in this case time. So how do you solve a second order ODE like this? One method is you just guess. You guess a solution that you think works. And based on your experience in life, if you were to take a block like this that were bouncing on a spring, what would it look like? It would look like, if you were to graph the position as a function of time, it would look like some kind of sinusoid, right? So that could be our guess. We just guess that the solution is some kind of sinusoid. How do you express this as a function? I'll just tell you and then explain. Okay, so this is one way to describe a sinusoid like this. This is the amplitude. Let me write it down. So amplitude. So amplitude is like this, right? So larger amplitude, smaller amplitude. So it's just kind of the vertical scaling. That's the amplitude. This will take some explaining. So from, let's say from here to here, this is the period. It's the period of time it takes that block to like go and bounce away and come back to its original position. That's the period of time. So let me say period t, period of time t, so that's in seconds. If you take the reciprocal of period, that's called frequency. Frequency f is just the reciprocal of period. And so the units would be 1/seconds, which we name that after hertz. So like say if the period were 10 seconds, then the frequency would just be the reciprocal, 0.1 hertz. Okay, and then there's something called angular frequency. So we call that omega, which is 2 pi f. And this is 2 pi radians times 1/second. So it would be radians per second. Okay, so for example here, this will just be 2 pi times 0.1. So 0.2 pi radians per second. All right, now how does that affect our sine wave, or sinusoid? Okay, so amplitude was this way. This angular frequency affects this horizontal scale. So if you take a look, this is a longer period, smaller angular frequency. This is a smaller period, higher angular frequency, right? So it just affects this scale. So that would be this, right? Affecting the horizontal scale. This affects the vertical scale. And one last thing here, this is called the phase angle. Phi, that's in radians. And that affects the horizontal kind of starting point, the position, so like this. For example, if I make the graph look just like that, that's a cosine. But what if I shift it toward the right 90 degrees? Now take a look. That's a sine. Let me move it 90 degrees more. That's a negative cosine. Move 90 degrees again. That's negative sine. I'll move 90 degrees more. And we're back to cosine. Okay, so this phase angle just shifts the wave left or right, depending on what number you put in there. Okay, so this is a good guess. We needed position, so this goes here, but we also need the second derivative. So let's take two derivatives of this thing. So one derivative, so dx dt, this happens to be the velocity, right? Is, let's take a derivative with respect to time, so that would be minus sine. And then don't forget the chain rule, see omega t, so times omega, I'll just put it over here. Okay, now let's take one more derivative, which is going to be the acceleration. Okay, so minus omega a, so derivative of sine, cosine. And chain rule again, so times omega, so omega squared. All right, now take a look at this. That's exactly x, right? So what we have here is the acceleration is minus omega squared x. And compare that to what we had over here. See over here? Acceleration was minus k over mx. Let me just jot that down over here. Now look at this. That means omega squared is k over m, or omega is square root of k over m. And then I made up numbers, right? Over here. If the spring constant is 25, the mass is 1, then for this example, omega would be square root of 25, 5. For this particular example, right? So we would know the answer. We know this is 5. But what is this and what is this? So because here we have 3 unknowns we need to figure out. So we got this one, that's 5. How about the amplitude and the phase angle? How do we get that? You use the initial conditions right here that I made up. These initial conditions. So how do we use the initial conditions? So the initial position was 0.1 meters. Okay, so let me copy this right here. Right, this is position. And we want the initial position. So when t equals 0. So just plug in t equals 0. Cosine, that would be 0. Like this. And it was the number I made up, 0.1 meters. Okay, so we have one equation with 2 unknowns. We need one more equation, which is the velocity here, because the other initial condition was the initial velocity. So the velocity at t equal to 0 would be minus omega a. If t equals 0, this would be sine phi. And the number I said was negative 0.2 meters per second. So now look. We have 2 equations, 2 unknowns, which means we can solve. What's a good way? I'll put this one divided by this one. I mean, there are a lot of ways you can solve. Minus 0.2, 0.1. So here you see that cancels. So minus omega sine over cosine is tangent. And, and then this is minus 2. Okay, and then omega we said was 5, right? So tan phi is minus 2 over minus 5. Oh, the minuses cancel. Right, so here we go. There, now we got the phase angle. And then you take that number and plug it right back in here. And then solve for the amplitude. Now we know all 3 of these. This, this, and this. So then you have the function, and that will be the answer. Okay? So give this a try, this problem a try. And then see if you can get through the entire thing yourself, all the way to the answer. And then let me know if you have questions, and I'll see you in the next video.